Like to go through this example and show you a few things like how to load a CSV file into our studio, how to run a test of normality, and how to make and understand a p-value probability expression. Okay, so this example comes from your notes. It's not exactly like the one in your assignment, but you should be able to use these skills to be able to do them in assignment type questions. Okay, so you go through, and in this case, you've got some raw data here. So what I mean by raw data is there are 10 data points, and we actually know which each of those 10 data points actually are. So not just giving us summarized values, but we actually have the data points. So um, I made a file and I downloaded it to my desktop. As long as you know where you are downloading your files, then you should be able to get to them. But in our studio here, if you want to import a data file that you've downloaded from like an assignment, for example, you can click on here, import dataset when you're under the environment tab. So here I'm just gonna, if it's a CSV file, I'm gonna use this one from TextBase. If it was an Excel file, perhaps you could use this, but our CSV file should be from text. Then you have to navigate to wherever it is that you've saved your file. For example, here I've saved mine on the desktop, so here my CSV file is there. And I'm going to press open. So here, R is going to do its best, excuse me, to try and understand the data in the way that it should. So one thing here is it's trying to see if the first point is actually a heading, and it thinks that it is, which in this case it is. So here, Mustang.prices is not a data point. You could force it to say no, which would mean that the heading is going to be a vertical one or V1, and then the first data point would be Mustang prices, but that would be confusing because that's not really a number. So R did guess correctly that in this case, Mustang prices is the name of a column, and then the rest of the values respond. The other thing that you can choose to do here is choose a name for your data file here. I'm going to choose the name just price. Okay, so after that's in there, then I can actually click import. So what that does then is here it calls a data frame price, and then it reads in the file. It also shows us what it looks like. So now you can see here under this data file that I've called price, then here I've got the name, which is Mustang.prices, and the corresponding rows. Okay, so that's great. We've got the data actually loaded inside of R. So you're going along and you're reading through the question and you're trying to develop your hypothesis. In this case, my hypothesis in the alternative, the sign is the less than. Why is the sign in the less than? Well, while I'm reading, I can see here the term less, not less than or equal, but just strictly less. So again, anything that contains the equal sign should go into the null hypothesis, but if you detect a direction that does not contain the equal sign, it should go into the alternative. And the other thing that we talked about in class is here, this is probably, if you've got the less than sign, then the complementary sign in the null should be the greater than or equal to. However, you're always allowed to use the equal sign, just the strictly equal sign in the null hypothesis, even if the sign in the alternative is in fact less than. So either this way of formulating your hypothesis or this way of formulating your hypothesis is correct. So at this point, we can actually perform the hypothesis test. There's many different ways to do that. But first, let's see if the data is actually normally distributed. So to do that, here I'm going to have to install a package. So when your uh, mouse is on the packages button, click that, and here I'm going to install a package called NORTest, which stands for normality test. Okay, so I'm going to select that. I'm going to say make sure install dependencies is clicked, and then I'm going to click that. Because I've already actually installed that, R is wondering if it wants me to update it because it's already been installed. So that's fine. I'll just re-go through the process of installing it. And then after it's installed, I am going to have to load it. So there's a number of ways to do that. If you want to just scroll, here are all my packages that I've downloaded, and I could scroll alphabetically to find NOR test, but I can also search for NOR test and make sure that this box is in fact clicked. When it is checked off like that, that means that the package is not only installed, but it's also loaded. So that's good. I've got my normality test package then installed and loaded. To run, there's many different types of normality tests, but right now, if you want to find the test of normality that your web work is going to use, then what I have to do is write the function ad.test. So that's called the Anderson-Darling test, which is a test of normality. And then what I need to do is actually access my data. So you'll remember that I called my data file price, and underneath this data file called price, the particular values that I want are in this column called Mustang price. So I first reference the fact that I am talking about a data frame called price, and then after that I put the dollar sign and then select the column. In my case, I only have one column, but if you had multiple columns, this is how you could say, yes, I'm coming from the data frame called price, but I'm particularly interested in the column called Mustang prices. Okay, so here at this point, if I press enter, I am going to get the Anderson-Darling normality test. I don't want to talk too much about this test in specifics, but here's the point. If my p-value is bigger than alpha, then I have normality. In this case, alpha is 5%. You can see here at the 5% level of significance, and my p-value is only about 2 and 2.4-ish% here. So what this is telling me is that this data does not appear to be normal. So like if I did a histogram, which I don't need to do, but if I did a histogram, then I wouldn't expect this to look very bell-shaped. Okay, it doesn't look very normal. And you can verify that by seeing that the p-value in the normality test is not bigger than alpha. Okay, so it doesn't look like that this data is really that normally distributed. However, we're still going to run the hypothesis test. Okay, so I mean, again, there are a number of ways to run the hypothesis test. One, here I could find the critical value. Um, in this case, I don't know what the population standard deviation. Actually, that's what we should do first. Is we should find what the mean of the data is. Okay, so again, I'm going to reference the data frame, and then I'm also going to reference the column. Okay, so that's what X bar is. That's the average of these sample points. I could find what the standard deviation is. Um, Okay, so here, that's the standard deviation. Now, is that the population standard deviation or is that the sample standard deviation? Here, we only have 10 samples. So when I took the standard deviation of those 10 samples, this is for sure not the population. This is not all Mustang prices ever. This is just the standard deviation of these particular 10 data points, which means that this standard deviation is for sure a sample standard deviation, not a population standard deviation, which is why when I run this test, I use a t-test and not a z-test. And also, if you're looking for how many data points, well, one thing you could do, you could see that they're labeled, that there are 10 here. You could also count them, I suppose. But here's also a function called length, where you can actually have R counted up for you. There are 10 of them. So I mean, right now when this column is pretty small, I guess it's not that bad to just scroll down and count them, or actually just see that there are 10 points. However, if you've got a very, very, very long data vector, then perhaps maybe using the length command is appropriate. Okay, so then from this point, I guess we could run the hypothesis test in a number of ways. One is we could actually find what the critical value is. So here, if the left tail here has 5%, then we can use the command qt 5%, where the degree of freedom must be n minus 1, so that's be 10 minus 1. This would be the critical value. To find the test statistic, of course, we'll use this formula and sub in what we've found, which is X bar, subtract the hypothesized value, divided by standard deviation, which we found, and root n. So here you could type that and use R sort of like a calculator there. And you can find, in this case, this would be the test statistic, and this is the critical value. So here's the critical value, which tells you where the rejection region is. And in this case, my test statistic is closer to the middle than it is to the end point with the rejection region, which means I am not in the rejection region. So I would fail to reject the null hypothesis. So it looks like here the average price for the Mustangs based on the sample is not significantly less than this number. Or in other words, I guess it is either greater than or equal to this number. It doesn't appear to be significantly less. Okay, so that's one way of doing it. Then to find the p-value, here, what the p-value is, it's the tail probability of the test statistic. Okay, so which tail? So here's the test statistic, right? So I just calculated this number, this negative 1.49. That's this test statistic here, whereas here's the critical value. So I want the tail probability of the test statistic. Notice that the tail probability of the critical value is going to be alpha, but the tail probability of the test statistic, that is called p-value. Okay, so which tail is it going to be? Is it going to be the left tail this way, or is it going to be the right tail this way? That is determined by the sign in your alternative hypothesis. So here I've got a less than test, so my tail should be on the left. If I had a greater than test, then my tail would be on the right. And if I had a two-tailed test, that would be the not equal to sign, then half of the p-value would be in the left, and then here the positive corresponding test statistic would have half of the p-value in the right. So really what I need to do here is find the area on the left side of the test statistic. So I can do that with this command here. Okay, so here instead of using the qt command, I'm going to use pt. That's going to find the probability on the left of this value, that is the test statistic. And again, the degree of freedom is n minus 1. So in this case, that would be 9. So that's going to get me the p-value. There are also other ways to run the hypothesis test, of course. Perhaps in class you've seen me use the BSDA package. So here with packages, I could also make sure that I've installed BSDA package. And again, I've already actually installed it, so it's kind of asking me if I want to reinstall it. And sure, I'll reinstall it just for the sake of this video. And then, of course, I have to make sure that it's loaded. So the box is checked, meaning it is loaded. And then I could use here this command now that I've loaded and installed BSDA, which is the tsum.test command. With my cursor inside the brackets, I can press tab, and then I can tell R what the sample average actually was. Okay, so let me just copy this so I don't have to type it all out. Copy that and paste it in here. Okay, so here, the sample average, which was X bar, is here. The sample standard deviation is here. The sample size was this. The sign in the alternative hypothesis was the less than sign. So you've got three options, all of which, if you're going to use any of them, they need to be inside the quotations. One is two dot-sided for a two-tailed test. One is less that you see here, or you could use greater than if it's the greater than sign. Under mu, this is where you actually put that the hypothesized value, so whatever value you've got in the hypothesis, and then also you can find what the confidence level is. And you can press enter, and this is going to give you then here the test statistic as well as the p-value, which we actually already calculated using alternative methods. So that's another additional way that you could possibly run the hypothesis test. There is another way in this case that you can. This only works when you have the raw data itself. So in this case, I actually have all 10 points and what those data points were. When you have raw data like that, you can also use a command called t-test, t.test. And in which case, what I need to do is put in where the data is located. And then I'll need to put the alternative sign is the less than sign. And I'll have to say that the hypothesized value, the value that I put into the hypothesis was that. And here I can also say what the confidence level is. And not surprisingly, it actually gives me the exact same data that I got from the other two methods of actually finding out this hypothesis test. So in this case, I've got three ways to sort of get the same results for the hypothesis test. Finally, what I want to do is to make sure that you can understand what the probability expression for the p-value is and what it means. So really, the p-value, again, is the tail probability of the test statistic. So here, my test statistic was negative 1.493. Okay, that's this value here. And the tail probability here, it's going to be the left tail again, because the sign in the alternative hypothesis is the less than sign. So here, this area here is the p-value. So the probability expression for p-value is, here I've got probability of, then you want to reference what distribution you're using. In this case, we are using a t distribution. Okay, so if we were using a z distribution, this letter would change from t to z. And in this case, we have 9 degrees of freedom. Why 9 degrees of freedom? Degrees of freedom were here the sample size -1. So here, what I'm saying is this is the probability of the distribution, which is the t distribution with 9 degrees of freedom. The probability that that is less than the test statistic. Okay, so here, what I'm saying is less than this value here, which is the test statistic. That probability is the p-value. So I found that here either using this method, where I found the probability of being on the left of the t-value, the test statistic. I could have found it from here. I could have found it from here, any of those ways. But here, this is the probability expression for the p-value. Now, how do you interpret the p-value? What does it mean? What it means is if the null hypothesis is true, which means if mu really is equal or greater than 1,315, then the probability of observing more evidence against the null hypothesis. Okay, so here's where the null hypothesis is in the center of the curve. Here's the test statistic that I found. So the probability of finding more evidence against the null hypothesis is actually in the tail that goes away from the middle. So here, what I'm saying is the left tail. Again, only left tail, because in this case, the sign in the alternative hypothesis is less than. But here, the probability of observing more evidence against the null hypothesis, so more area away from the null. Okay, so here, this tail probability is this number, which happens to be the p-value. I hope this was helpful and that you can apply this to your actual question. Thanks for listening.